Good morning. Hello and happy weekend. Yep, still weekend. Honestly, I don't even know what date it is anymore. Everything's just bleeding together. Oops, let me move my face. So this week we jump into one of my favorite topics, and one of the reasons I got into science in the first place, climate change. We got a lot to get through today. Um, This topic, or this week, and my presentation in particular, will primarily talk about the science behind climate change. But some of your assignments this week will sort of discuss the political side, but also just the effects of climate change globally and more culturally and anthropologically. So this is more about the science. However, I do want to talk about uh, some aspects of climate that have been coming up more and more prominently over the last few years. And I have had the privilege to go to a few conferences regarding climate science, and climate change, and educating different age groups. I do work with K through 12 kiddos in the summer, so this is all about sort of how to mitigate climate anxiety uh, with different age groups, and I've learned a couple different ways to approach this. But just so you are familiar with this term, if you're not already, climate anxiety is essentially the feeling of anxiety around the topic of climate change. And a survey of 10,000 16 to 24-year-olds, so your age group, your generation, in over 10 countries found that 59% of these kids, of you guys, you're not kids, I apologize, of these humans were very or extremely worried, and 84% were at least moderately worried about climate change. More than 50% of these students, or of these humans, reported each of the following emotions: sad, anxious, angry, powerless, helpless, and guilty. And there are similar trends for even younger children, for kindergarten through high school, which is crazy to me. When I was, in middle school and high school, this was a topic that was important, but it was not nearly as predominant as it is now. And it was not nearly on the tip of everyone's tongue as it is now. Um, and so I want to address this climate anxiety. How do you mitigate that? How do you approach this and assess this without feeling those emotions that are sad and anxious and angry and powerless and helpless? And there's a few ways to grow in your environmental literacy. Uh, and environmental literacy is defined as the capacity to engage in making decisions that result in changing your local environmental capacity and your understanding of environmental justice. So with this sentence, I want to preface that the next topics that we cover after today are environmental and human impacts, and sort of the demographics that a lot of these climatic problems are addressing. And that is what environmental justice is. It's understanding that the demographics who are primarily affected by climate change are BIPOC, and developing countries. The individual, so another definition is the individual and collective understanding, your skills, cultural awareness, motivation, and practice of environmental stewardship resulting in responsible decisions that consider relationships to our planet Earth's communities and our future generations. So I know this was a lot of words, and these were words and definitions that I got from some of these conferences that I went to. And there are a lot of different definitions about environmental literacy. But what I want to do in this class, now that we've talked about the baselines of evolution and ecology, I want to talk about how you can grow in your understanding of climate change, how you can look at data sets and objectively define these situations and scenarios yourself without becoming bipartisan in one way or another. It's so politically driven right now, that it can get really bleak and it can get really dark. And I was talking to one of my supervisors, and I know I am very biased in my uh, sort of my take on climate change, and I'm going to try very hard not to be, because it is important to just understand, to take in the facts, look at the data, take in the facts. Don't consider a political side when you're looking at climate change. Um, and I want you guys to learn how to recognize data and facts to come up with your own decisions and to move forward into your own decision making. So something that I have also learned in my education through climate change is to build a strong sense of local space and community in your local environment. So start small. One of my former bosses, who I really loved in theater, I fucked up a wig one day, like bad. I fucked up really curly hair and it was a mat and it was going to take hours to comb and I was just like bawling. It was one of my first days of work. She comes over to me and she's like, how do you eat an elephant? And I was like, I don't fucking know. How do you eat an elephant? She's like, one bite at a time. If you see a big problem and it's overwhelming and it is terrifying, you start small. And it's still to this day some of the best advice I've ever gotten. And that also includes something like climate. It can be overwhelming to see these horrible news articles with these clickbait titles and all of these overwhelming, like everything's on fire and we're all going to die. It can be really overwhelming. And that is what is causing this climate anxiety. And that is what is causing a lot of panic and a lot of fear. My best advice to you, if you are feeling this anxiety and you are feeling the stress and this sense of hopelessness and despair, start small. So grow your knowledge on individual concepts regarding your local space, your local region, and your local government. One thing I'm really excited about for the rest of this term is I really tried to incorporate a lot of our local being Skagit. Hopefully you are within the Skagit realm, and if you're not, that's okay. But I'm really trying to incorporate our local scenarios so you can start there, start gaining your knowledge within our local space, and growing your education base with that. And then you can build an understanding regarding the broader community in a geospatial sense. So if we start small and you start with Skagit, right? And you gain a better understanding about Skagit's environment and our local leadership and our local policies and how we're mitigating climate change, then you can maybe jump to a Washington scale and look at the state as a whole. What are we doing as a state? What are we doing as a local government? And then we can expand to a broader scale with the United States, and then we can expand to a global scale. So start small, see what you can do to help your local community and your local area in regards to climate, and what are you doing to recycle or to help plastic usage or to compost or to garden. Start there. Okay, take a tiny little bite of that elephant and then we can jump onto global issues. And I say this as if it's so easy to do, right? It's not. It's really not. And I do talk about global scale or global sense of climatic things going on throughout the world, because I also want you to know that we're going to learn about those as well. But you as an individual, to help mitigate your own climate anxiety, start small. We're going to learn about local and broad scale issues so that you can gain a better sense of what's happening around the world. And once you have that literacy, we can move forward and work smaller. Okay? Oh, I added a slide, but oh, no, I didn't. Ha! I didn't talk about this. Emily. So I put this up here. This woman, her name is Ellen Kelsey, and she wrote this really cool book called Hope Matters. She did a talk at Western last year. Last term? I don't remember if it was last term or last year. Either way, it was last year, I guess. But she essentially, so she wrote this book and it's about mitigating climate anxiety. How do you find hope in a space where it's a lot of clickbait and fear and anxiety? And it's her philosophy is essentially why changing the way we think is critical to solving the environmental crisis. She's great. Highly recommend this book. It's a skinny book. But this was her website. You can go to her website. She also has like a couple YouTube videos you can watch where she talks about climate anxiety. So she's a great resource to go to. I also got this book that I wanted to show you. It's called Hurricane Lizards and Plastic Squids. So this was written by Thor Hansen. He's actually a professor at Western. And he teaches the dinosaur. There's like this famous dinosaur class in the geology department where you can learn about dinosaurs. And he teaches it. It's online. I've never actually met him. But he wrote this book, and it's about the biology of climate change and how biology is changing, how different species are evolving to climate change. And then finally, this is another really great book. It's a Pulitzer Prize winner, The Sixth Extinction. And it talks essentially about how in the past, in Earth's geologic history, there have been 5 major mass extinctions, and we are moving towards the 6th extinction, which is us. And it's a little more bleak than the other two, but it's also very informative, and it really provides a really great overview of what humans are doing, but also what we can do. It's a really great book. Highly recommend. I would start here and then read this one and then read this one in that order to go from, okay, it's bleak, and then, but here's how things are being affected, and then finally, how do we fix it internally? Okay, so that's all I'm going to say there. Let's start in on the science of climate. Because understanding how the climate is changing is going to be really important to understanding how to mitigate it. So to do that, the first thing we have to look at are the layers of the atmosphere. So we have 2 graphs here. I'm going to start with this left one. There are these 5 layers of the atmosphere. Troposphere, this is the layer that we're in currently. And actually, if you get to the top of the troposphere, this is as high as jets fly. So if you've been in a plane, it feels really high, right? You're at 39,000 feet. And this is essentially, they fly up here because air, I don't want to say air density, but air density is, air pressure, I guess is the right word, but the air up here is so much less compact that jets can fly up here and it's much more fuel efficient, right? So that's why they fly this high. They get to this altitude so that it's much more fuel efficient. So this is the troposphere. The next one above that is the stratosphere. We do put weather balloons up this high to test for weather. This is where meteors will light on fire because that's where our air pressure begins to get heavier, denser. Our mesosphere, thermosphere. So if you were around last year, year before, excuse me, and you saw the beautiful auroras, they were so cool. It was so cool to see that this far south. The thermosphere is where this occurs, and it has to do with the way that the solar flares end up hitting the thermosphere. It's a whole thing. I won't go into it. I don't even fully understand it, but we get these beautiful light depictions, and they're called auroras. And then finally, the exosphere. So this is where we orbit our space stations and our satellites. So the exosphere is still technically part of the Earth's atmosphere, and it has a gravitational pull as part of this layer, which is why we can orbit space stations and satellites in this part of the atmosphere. And then beyond that is space. So we have a lot of layers here. We're going to mostly focus on troposphere and stratosphere in terms of climate change. The others are important, but these 2 are the ones that we're mostly going to talk about today. And this graph over here, I really like. We're going to see it again later in this slideshow. What we're seeing is we're seeing how temperature changes between the different layers of the atmosphere. So what we're going to understand today is how the temperature actually decreases in the troposphere as it gets higher up. If you've ever hiked a mountain and you get to the top and you're like, wow, it's so cold up here. I wonder why that is. That is because heat is actually being released from Earth's surface, which we'll talk about in the next few slides. So it's going to be warmer at the surface of Earth, and then the higher we go up, the heat declines as we go up. So it gets cooler. It gets colder. In the stratosphere, it actually rises a little bit. And in the mesosphere, it lowers a little bit. And then in the thermosphere, it rises again. So we have this sort of cyclical pattern between the different spheres and layers of changing temperatures. Why is that? Oh, so glad you asked. Okay, let me move my face again. Okay, so the sun, this is where we get our energy. This is where we get our heat. This is where we get all of the important facets that bring our Earth's life alive, right? The sun provides all of our energy in a lot of capacity. So incoming solar energy, which is our heat, it's a wavelength, comes in at 100%. 70% of that solar energy is absorbed by the Earth's surface. The Earth, which is, geologically profound, has a lot of rocks, material. It actually absorbs that heat. But not all of that heat is absorbed into the Earth, right? So 6% is reflected back into the atmosphere from other layers of the atmosphere. 20% is reflected from clouds, which we're going to talk about later too. And then some of it's just reflected off the Earth's surface itself. So of that 70% that is absorbed into Earth, 6% is then radiated to space from Earth. 64% is radiated to space from clouds and atmosphere, and that is the 70% thermal energy that we have. It comes in as solar radiation, and it is emitted actually as infrared radiation. So they're two different wavelengths. They're two different types of energy. One is coming in and one is going out. And that's going to be important for later. I think we talk infrared. Maybe not. Regardless, two different types of energy. One is coming in, it's being absorbed by Earth's surface, and that is then being re-emitted back out into space as infrared energy. So let's talk about the difference between weather versus climate. This has always been a big topic, and this has always been a big argument in climate change. Do I show the picture of the dude? So I should remember this. I think I bring it up in policy, actually. Hold on, okay, I wanted to find this. I'm not gonna show it here, but in 2015, there was a senator, James Inhofe, I don't know how to say it, from Oklahoma, who came into Congress and he brought a snowball with him. And he was like, what do you mean climate is changing? What do you mean climate is warming and we have global warming? I have a snowball. That means that this whole argument is wrong. And it was a really silly argument to try to have. You can look this up. I literally just Googled politician who brought a snowball into Congress, and it's the first thing that pops up. Because I remember when it happened. And when it did, it's a very poor argument because he was talking about a weather event. So weather is the state of the atmosphere at a particular specific and well-defined point in space and time. It is generally short-term. It can be from minutes to days. And weather forecasts have little statistical value beyond roughly 5 to 10 days. So I don't know if you have a weather app and you go on regularly and you look out 2 weeks in advance and you're like, wow, it's supposed to rain in 2 weeks. And then 2 weeks happens and you're like, why isn't it raining? That's what it said 2 weeks ago. It's because it's based on a model. And what a model is it projects data that we have currently into the future. And so some of those models might change. They might not be perfectly accurate, but they're as close to accuracy as we can get by using data that we have now. So beyond 5 to 10 days, it's really hard to have that sense of accuracy. And it's non-linear and chaotic, but still predictable behavior associated with the physical evolution of the initial conditions into future conditions. So that's what I mean when I say they use data that we have now and they project that into the future using models, using a whole lot of math that I will never learn because gross. Meteorologists actually have to take some crazy calculus for this process because it's very math-based, very, very mathematically heavy. So I have a lot of respect for meteorologists. I know a lot of people are like, wow, they can't do their job right because the weather is different 2 weeks from now. And yeah, well, you try to do it. I could. So this is weather. And when it's saying that it is a well-defined point in space and time, this is a local setting. Weather is local. And so this senator who brought in a snowball in 2015 was experiencing a weather event. He was experiencing a snowstorm in a time of climatic change. But climate is generally long-term. So we consider climate on years to decades of a time scale. It involves components of the Earth's system other than just the atmosphere. And this is a defining characteristic of climate. It is expected, repeatable, responds predictably to a forcing, which we'll talk about shortly. And it's generally predictable on long time scales. So this is decades to centuries and large regional and larger spatial scales. So this is how we see the United States' climate or the global climate. This is something that is occurring over such a long period of time that weather events are happening in that long period of time that have been brought on by these climatic changes. So weather is small, think short time span and small local regionalized area. And then climate is long-term scale. We're thinking decades, even centuries. Well, maybe not centuries, but decades and beyond, and very wide spatial scale, whole globe. Okay, that's the major difference between the two. So a climate I mentioned in the last slide is brought on and uses different components of Earth's system other than just the atmosphere. So there are 5 major climate components that really affect climate and climate change. And those are going to be the cryosphere. So this is ice. These are our polar ice caps. You got Antarctica in the south, you have Greenland and the Arctic in the north. Our biosphere, so our mass of trees. But also remember in ecology, I talked about how algae actually produces approximately 70% of Earth's oxygen. So algae falls into biosphere. Our geosphere. And our geosphere is really important on super long range scales. It is both a carbon sink, which means that it takes in a lot of carbon from the atmosphere over a very long period of time, millions, if not billions of years. Mostly millions to hundreds of millions of years. And it does produce some of our greenhouse gases. Volcanism produces a lot of sulfuric acid. It also produces a lot of carbon and carbon dioxide, but at a much smaller scale than what you would think. And then hydrosphere is our waterways, our ocean. So those are the 5 components that comprise our climate system. Boop. Oh, and then I dive into, sorry, I got so ahead of myself. Okay, I'll go through this fast and I'll let you kind of read through it on your own. Atmosphere, hydrosphere, variations in temp and salinity, cryosphere. This is a consistent part of the climate system, ice sheets and glaciers, biosphere. Yeah, I'm going to let you read through this yourself. Sorry, I got ahead of myself. Boop. Okay. Climate. Different parts of the world have different climates, and we're going to look at what those are. Some parts of the world are hot and rainy nearly every single day. Gosh, it feels sometimes like Bellingham's like that. Although right now it's January and it's been sunny for like 2 straight weeks. Yay. Others are cold and snow covered most of the year. So our climate systems are actually in a latitudinal pattern. So here's our globe. If you have never seen lines of latitude and longitude, our up and down or north to south lines are called lines of longitude. Remember them, they are long. Lines of longitude. Our lines that go across left to right or east to west, these are our lines of latitude. And I remember latitude they are like the rungs of a ladder. They go up and down, but the lines themselves actually move east to west. These lines are parallel to our equator, which is the very center of the Earth. And the equator has a line of latitude at 0 degrees. I know Bellingham, I imagine Skagit's pretty close to Bellingham. Bellingham is in a line of latitude of 48 degrees. So we're like here. Okay. And these climate systems are based on these lines of latitude. So tropical is going to be right around the equator. It's hot and humid. Average temps are greater than 64 degrees Fahrenheit year-round, but they also have high amount of precipitation. And that's because if you have that kind of heat, that heat is going to evaporate the water, like the ocean water. It will evaporate the water, which has to rain back down. So this area has a lot of rain. 20 degrees-ish in this area, it's our yellow. This is dry. These climate zones are so dry because moisture is rapidly evaporating from the air because of the heat, and there is little precipitation. This also has to do with sort of the wind currents. They're called wind cells and atmospheric cells. We don't dive into that in this class. I teach another class where we dive a little bit into atmospheric sciences, but those also drive these climate systems too. Because remember, climate is driven by more than just one factor, and the entire Earth system, including atmosphere, hydrosphere, cryosphere, geosphere, and biosphere. Temperate, which is this greenish zone here. This is usually a warm and humid area with thunderstorms and mild winters. Continental. These regions have warm to cool summers and very cold winters. In the winter, the zone can experience snowstorms, strong winds, and very cold temperatures, sometimes falling below negative 22 degrees Fahrenheit. And then finally, you have polar climates. And in polar climates, it's super cold. Even in summer, the temperatures really never go higher than 50 degrees Celsius. You have a lot of ice, and it's very dry. One thing I want to note about this map that I really liked, which is why I showed this one first, is you can see that it's not an abrupt end to these climates. They sort of like meld into each other. They sort of ombre into each other, right? And that's because there's not an abrupt ending to these climates. They fade into one another, really kind of transitionally, if that makes sense. So there's a lot of differences between some of these areas, based on topography and some other things, but they meld into one another. There's not an abrupt change. So this is Köppen climate zones, and I actually have a much better map than this one. I put this one here anyways because it matches the colors here, and it's general for the United States. So you'll know we are sort of dry, which I don't necessarily agree with, but that's what the Köppen map says. Science is objective, but there can be subjective takes on that objectivity. What that means is that you'll get data, you'll produce data based on your experiments. However, that data might be interpreted in different ways by different scientists. Not all branches of science necessarily fight over different interpretations. Geology, actually, there's plenty of interpretation that goes into geology, which is really fun. And climate is another one that people might argue about. And it's changing so rapidly that our climate systems might also be changing. But anyways, my whole point here is that you'll see that we have this nice gradation of changing climate systems based on latitude. But you'll know when we get to the US, there's a whole bunch of different ones here, right? And that has to do with topography, the different wind systems that we're seeing, the precipitation. So for your lab this week, you're actually going to look at this, which is global. This shows just the US, and I like this one. However, this shows the main climates of the entire world, which is really useful. And you're going to look at patterns throughout this. So I'm not going to talk much about this, but you are going to use this Köppen climate classification map in your lab this week. Again, labs are about analyzing and interpreting data. This next slide is one of my faves. I don't know if you're a Star Wars fan. I love Star Wars. I haven't watched it in a minute, actually. And I have opinions about the new movies, obviously, as we all, I'm sure, do. However, when George Lucas was writing this series, this movie system, he came up with these planets that were entirely climatic planets. And I don't disagree with some of his ideas. So on the left is Hoth, right? Yeah, this is Hoth. This is the ice planet Hoth that Luke Skywalker goes on in the second movie. I don't remember. I should know this, but I don't. And it's all ice. The entire planet is covered in ice. And then over here is Tatooine. This is Luke Skywalker's home planet, and it's a desert planet, right? So it's all sand. This is something like you'd see with Dune, too. So the movie Dune that came out, the entire planet is a desert planet. And then this is Dagobah. So Dagobah is the tropical forest that Luke Skywalker goes to get trained from Yoda. And this planet is all tropical. And what I love about this is it's silly and obviously it's not scientifically, this whole series is not scientifically accurate at all, but who cares? But what I do love is there are actually planets that we have observed that have these sort of entire planet systems. And I say planet, I know that there is a moon, one of Saturn's moon, watch me butcher this name, Euclideus? I don't remember. It's entirely ice. And we've discovered that it's like kilometer thick ice. And a lot of that ice is actually covered over a water system that has a lot of methane in it. So we're seeking life on this planet. And there's a planet, or there's a moon. One of Jupiter's moon is also covered in ice. So, like, it's not unrealistic to say that these planets would exist. They are silly. Not all life would be able to exist on some of these planets. Like, really, you're gonna have civilizations on a completely ice planet where there's no resources at all? Same with a desert planet. I question this. Whatever. I'm not here to rewrite fiction. But I wanted to bring this up because it's just fun. Okay, so let's talk about the greenhouse effect. We have talked about climate systems, and we have talked about where climates fall on Earth's map. But let's talk about the greenhouse effect. So how is this climate changing? So we talked about solar radiation, right? So solar radiation is direct radiation from the sun, and it's passing through our clear atmosphere onto Earth. Some of that is being absorbed by Earth's surface, right? And it is actually warming the surface of the Earth this way. Some of it's reflected by the Earth, and some of it's reflected by the atmosphere. We all saw this in the first map that I showed. However, the heat that is absorbed by the Earth is then re-emitted as infrared radiation, which heats the literal surface of the Earth. So if we walk outside right now and it's warm, it's not warm, it's January, but if it was, that is actually the heat coming from the Earth. Some of the infrared radiation passes through the atmosphere and goes right back out into space. Some of it is what we call refracted, so it hits the atmosphere and refracts, but still goes out to space. However, some of that heat is actually reabsorbed or reflected from the atmosphere and comes back into Earth and continues to heat the surface of the Earth. The effect of this is to continue to warm Earth's surface and lower temperature. So if you've ever gone outside and it's clear and there's no clouds in the sky and it's January, like literally today, this is what I'm talking about for today, it feels really fucking cold. It is currently, oh, it's 43 degrees outside. I thought it was like 30. But it feels really cold out there. But then let's say you go outside on the same day and all of a sudden all these clouds show up. It's going to feel warmer. And that's because when the heat is emitted from Earth's surface, those clouds act as insulation. And so it feels warmer sometimes when there are clouds in the sky because that heat will reflect off of those clouds back into Earth. But when there's no cloud cover in the sky, it just goes straight back up into Earth. Some of it's reflected, but mostly straight back up into the atmosphere. So those clouds work as insulation. They work as a blanket. And the reason that we're not an ice planet like Hoth, cracked me up, is because we have a lot of gases in our atmosphere that are helping reflect that heat back into the atmosphere. So clouds do this for sure. And that is something visually that we can see, that we can recognize. But there are some gases in the atmosphere that we don't visually see that are clear, that work to also reflect the heat back into the atmosphere. And so these are those gases. So water vapor is actually the most dominant greenhouse gas. What are clouds? Water vapor. Precipitation, especially in the summer when the sun is able to heat the earth a little bit longer because it's in the sky a little bit longer, especially in PNW, Pacific Northwest. A lot of that water is evaporated, turns into rain, creates clouds. This is actually our biggest, not biggest physically, but our most dominant greenhouse gas, water vapor, clouds. Not just in cloud form. Sometimes it's just water vapor hanging in the air before they form clouds. And then our second most abundant is carbon dioxide. So perhaps you have heard about CO2 being the biggest greenhouse gas. It is by far the most problematic greenhouse gas. Water vapor is a natural, and I mean carbon dioxide is also a natural entity as well. But water vapor is so natural. Hold on, I want to make sure I talk about this. I don't think I do, so I'll talk about it now. It has what we call a residence time. So different gases remain in the atmosphere for different amounts of time. Water vapor, while it is our most abundant greenhouse gas, when it evaporates, it only remains in the atmosphere for a couple days, maybe, if that. This is what we call a residence time. So that residence time is very short. it's only in the atmosphere for a few days. That means, hypothetically, crazy hypothetical. Let's say let's get rid of all of the water vapor to get rid of greenhouse gases or to lessen our greenhouse gas. And from some miraculous scientific entity, we're able to get rid of water vapor. In about 2 to 3 days, we would start to see a change of heat retention, which it would cool the earth. Obviously, that's not going to happen. So it would only take 2 or 3 days to start seeing a change in our atmosphere and our climate. Okay, so that's why water vapor, while it is the most abundant, it's not the most dangerous. Carbon dioxide has a residence time of about 10 years. So that means that carbon dioxide, after it has been emitted into the atmosphere, whether from natural sources like volcanoes or human anthropogenic sources like gasoline or fossil fuels or coal, any of those, that will remain in the atmosphere for 10 years. So even if by some miracle we're like, all right, let's stop emitting carbon dioxide, we won't actually see a change in the climate for approximately 10 years. That is why it is so problematic. And in those 10 years, our climatic systems will continue to worsen until that carbon dioxide is out fully. And obviously, this is not a realistic scenario. We are not about to get rid of our carbon dioxide fully. So that carbon dioxide is just going to continue to build. So here's CO2 down here. And carbon dioxide, it's a molecule, right? So there's one carbon molecule to every 2 oxygen molecules. So our red balls here represent oxygen, and then our carbon is this little black ball in the middle. And what happens physically is this carbon molecule has hold on, I have to think about this, positive charge? Yes. And oxygen has a negative charge. And that's a lot of chemistry that I won't get into. But what I want you to understand is that think about if you have a magnet and you try to put those 2 magnets together, they kind of repel each other if they're the same charge, right? So if you have a positive end of a magnet and another positive end of a magnet, and you try to put them together, they like repel each other. They don't want to touch, right? But if you switch one around and you have the negative side over here and then the positive side here, they stick. They go, oh, hey, we're BFFs. Opposite charges attract. It's the same with batteries, right? If you put a battery pack into your remote, you want the positive end touching the negative end. So what you have here is you have a positively charged carbon, pretty sure it's positive, and then a negatively charged oxygen. Okay, I had to double check because I was stressing myself out there. I didn't want to give you the wrong answer, and I was correct. Oxygen is negatively charged and carbon is positively charged. Okay, back to it. So what you have is this carbon in the middle, and it's being repelled by these 2 forces on either end. And so what it does is it vibrates really fast, like this. And so as it vibrates, that vibrating force is actually what is reflecting the heat back into Earth's surface. The heat will hit a molecule like this that's moving really fast, and it goes right back onto Earth's surface. It is what we call a straight molecule. You'll see that it's straight across, and it vibrates really fast. Okay. So that is why carbon dioxide is a greenhouse gas. Conversely, over here, here's our water molecule. And the reason water vapor is a greenhouse gas is it's actually bent. It's like a V. And that also has to do with the charges of the hydrogen molecules, which are these 2 here, and then our oxygen here. Has to do with those charges. It's bent. And similarly, this one doesn't move like carbon dioxide does. It doesn't vibrate like this, but it is bent, which also reflects that heat. Okay. So those are our 2 big ones, our 2 big greenhouse gases. And then we have methane, which is CH4. So it's 1 carbon and 4 hydrogens. It's actually shaped like this. It's like a big X. So it also is forcing materials back into Earth because of its shape. And methane, there's only 10%. So 10% of our greenhouse gases are methane. And this one by far has the longest residence time. I want to say it's like 20 years, 25 years that it will stay in the atmosphere. It's not as abundant, mind you, but it does have the highest residence time. Ozone is also really problematic. That means there's three oxygen molecules, but only 5% of all greenhouse gases are represented by ozone. And then same with the others, chlorofluorocarbons, HFCs, perfluorocarbons. Whew, yeah, I know I'm an organic chemist, but some of those words, man. So all of these are our greenhouse gases, but the ones that we focus on primarily are water vapor and carbon dioxide, and sometimes methane if we're getting crazy. So this is where all of our carbon is stored, and that carbon goes into carbon dioxide emissions, right? As a gas, carbon usually will bond with oxygen as to form that gas. Carbon by itself is not going to be a gas, but it will bond with oxygen and create carbon dioxide. So these blue, I'm not going to go through all of them, but these blue words are what we call, oh man, stocks. I also call them reservoirs. So these are where our carbon is stored. By far, the most amount of carbon on Earth is going to be in Earth's crust, our crust, in the rocks. Carbonaceous rocks. And the red is what we call the fluxes, or our budget. So this is where we see carbon either going into reservoirs or coming out of reservoirs. So how much is being taken in by the ocean? 92, and it's in billions of tons. So 92 gigatons of carbon is going into the ocean, and 90% of it is being re-emitted into the atmosphere as CO2. And here's our reservoir for our atmosphere. We have 850 gigatons of carbon in our atmosphere right now. So I just think it's a really interesting map to look at. It's a calculation essentially, and a flux. This is my favorite graph of all time. I do love it. So this is what we call the Keeling curve. It began with John Keeling in 1954, I think it was 1954, 1956. So this guy, he was down at Scripps University in San Diego, and he was like, I want to measure all of the carbon dioxide in the atmosphere every single day for as long as I can. And so he chose to go to Mauna Loa, which is the big island in Hawaii. If you are not familiar with that, there's a big observatory on top of Mauna Loa right now. And one of the scientific processes that they're doing on that mountaintop is measuring carbon dioxide levels in the atmosphere every single day. And so he did this. And when he started it, he was actively doing like actual chemistry, like taking beakers and pouring solutions into beakers and measuring all the carbon. It was like crazy. He was doing this multiple times a day, every day. And then technology evolved. And now they're measuring it with very accurate instruments up on Mauna Loa. And his son, Ralph Keeling, who I have had the pleasure of meeting, he's just delightful. He's so sweet, very awkward and silly, but super sweet guy. He took over his father's project, and he's working on this now too. And he is also a geochemist, so he measures the atmosphere in the ocean and its emittance into the atmosphere. And what he found was this line, and it's a very famous graph in climate science. I don't remember if he won the Nobel Prize for it or not. He might have just been nominated. I should look. Regardless, so he has delivered this graph. We are still measuring today. And he chose Mauna Loa because it is not around human activity. I mean, besides Hawaii. And it's in the northern hemisphere. And he chose the northern hemisphere. It's close to the equator, mind you, but he chose the northern hemisphere because if you look, most of human activity is in the northern hemisphere. Actually, let's just, can I not go back? Okay, you're gonna hate me. Sorry. Oh, this is fine. So here's the equator. Think about the population of humans within the northern hemisphere. We're all here. This is Europe. India has the highest population. That's not India. That's Saudi Arabia. This is embarrassing. This is India. India has the highest population of humans on Earth. Japan has another dense population of humans. So most of human population is up here. So he chose Mauna Loa. Here's Hawaii right here. He chose this area because it's in the northern hemisphere, and he wanted to accurately gain measurements from human activities, but far away from human activity. So it's a well-mixed experiment, which means that he's getting emissions from everywhere in the northern hemisphere, not just one location. So if he was located on Mount Everest, which is here, yes, it's high, but he'd really be getting a sort of biased or skewed data set from this region. Now that he's over here, he has atmospheric winds to sort of move that carbon dioxide and mix it really well, so he gets a more accurate depiction of CO2 measurements here. And yes, there are going to still be some problems with that, right? He might get a higher skew based on activity here and based on activity here. However, it's still going to be better mixed than any other continental area in the world. So that's why he chose Mauna Loa. Oh, back to here. So what we're seeing here is we're seeing this cyclical pattern, the sinusoidal change. That's the up, down, up, down, up, down. But it is headed up. Boop, boop, boop. And what we also note is this trend going upward. It's not straight. It's not linear. If it were, it would go, hopefully you can see my arrow, like this. What we're seeing is what we call logarithmic is one. Oh my God, why can I not think of the name? Exponential. Whew, I knew it started with an E. I was going to get there. It's an exponential trend, which means that it is starting to go up at a much faster rate than it is linearly. Okay, so we're starting to see this curve go up much faster, which means we're going to start to see more vertical trends faster. It's a scary trend to see, honestly. And what we have on the left is carbon dioxide concentration in parts per million, that's ppm. And what that means is that if I had a little box and I put 1,000,000 little molecules of air into that box, 330 of them here at the bottom would be carbon dioxide, or 400 of them here would be carbon dioxide. So in a way, that's relieving, right? We're only seeing 400 carbon dioxide molecules in a box of 1,000,000 molecules. However, that's significant enough. We see a change of approximately, 75 or more parts per million just in the last, math, 4, 5, 6 decades. Okay, so this is the same graph. This is this graph, but small. So you can see it a little closer. This black line indicates the general trend of this carbon dioxide mixture. So we're rising, right? This is from 2017 to 2023. And then we see the cycle. So why do we have this cycle? Why is it cyclical? And why is it staying the same almost every year, which is actually really cool that it's doing that. Okay, so this is emittance of carbon dioxide. This is the amount of carbon dioxide we have in our atmosphere. And this is happening every year. You see, we have about here is 2018, and about 2019, it's hitting the same level or the same place on this sinusoidal graph. Not in the same parts per million, but on the sinusoidal graph. So what we're seeing are annual fluctuations of seasonal changes of plant life. How cool is that? Okay, so let's break that down because that was a weird way of saying that. We're seeing photosynthesis and respiration. So when we see an increase of carbon dioxide like this, that means that more carbon dioxide is being emitted into the atmosphere. That is fall. That is autumn. That is when all of our plant life in the northern hemisphere dies and hibernates, drops its leaves, and all of those leaves are decomposing. And as those leaves decompose, they emit carbon dioxide. This is a rise in carbon dioxide. This is fall. This is autumn. Conversely, we see an intake of that carbon dioxide every single year as well. This is spring. This is when those plants are beginning to grow again, and they are taking in all of the carbon from the atmosphere and turning it into biomass so they can grow, and they can grow beautiful leaves, and they're producing oxygen for us to breathe. So what we see are these annual cycles of photosynthesis. Photosynthesis is going down, and then respiration is going up, and photosynthesis and respiration. which is so cool. Like, that's so cool that we get these carbon dioxide readings on such an intricate scale that we see it like this. How cool is that? So cool. I just think it's incredible. And so I met Ralph Keeling, who's the son of John Keeling, because I was going to do a PhD with him. Um, and so we chatted about his PhD projects. He's all about modeling, though, which is like all calculus. And I was like, that's not going to work with me. He was a very nice guy. I would have loved to work with him, but I just did not have it in me to do 5 years of modeling and calculus. But it was cool to meet him. So, anyways, that is this Keeling graph. That's this Keeling curve. And what we're seeing is while annual cycles are staying approximately the same every single year, they're also rising. The amount of CO2 is rising. So we are emitting more CO2 into our atmosphere every year. This graph's really cool. I'm not going to dive too hard into it. What we're seeing is it's well mixed greenhouse gases. So remember how I talked about mixing? And while it shows Mauna Loa, boop, over here-ish. Oh, nope, there it is. It's this little dark blue dot. So while I chose Mauna Loa, because it has these well-mixed carbon dioxide greenhouse gases, this is because the bluer colors are better mixed than some of these brighter colors. And these brighter colors are less mixed, which means that we're seeing these temperature anomalies. And an anomaly, which I talk about soon, I talk about at the very end. But an anomaly essentially is a change from the norm. So our normal temperature here, this a 0.0 anomaly just means there's no change. But what we're seeing with these well mixed, or not mixed, pardon me, gases, is we're seeing a change in temperature. I lied to you. I lied to you. Sorry, I just read this. The color has the entire Earth is well mixed in this capacity. I apologize. What we're seeing still are the anomalies. So these anomalies are temperature anomalies across the world. But all of the greenhouse gases are well mixed here. Ooh, sorry, my bad. These graphs can be really tricky to read sometimes, which is why I was like, I'm not going to dwell on it, and then I dwelled on it. Sorry, guys. It is a really cool graph, though. So it's showing how these temperatures are changing across the globe. So let's talk about forcings. I told you I was going to talk about forcings because in one of the first slides about climate and defining climate, one of the sentences was, it's expected and repeatable, and it responds predictably to a forcing. So that was part of the definition of climate. And I said I'd come back to it. So this is me coming back to it. What is a forcing? What does that mean, and how does it correlate to climate? So a forcing is what happens when the amount of energy that enters the Earth's atmosphere is different from the amount that leaves it. Think about like a budget. Think about like your monthly spending budget. If you receive $100 in a paycheck, but your rent is $120, you're spending more than you receive. But in our case, we're actually spending less. So we're getting $100, 100 carbon dioxides, and we're emitting that into the atmosphere. But we're only spending 80% of that, which means we have more left behind in the atmosphere. That's a forcing. The change in energy balance in Earth's atmosphere. Incoming power should always equal outgoing power, but it doesn't. It doesn't. And so, my face here, this graph here is showing the different forcings in Earth's system. So our biggest forcing by far is carbon dioxide. What this means is that it is a positive force. Doesn't mean a good force. It just means that we have an overabundance amount of this material that we do not have an equal power dynamic. So we're putting out more carbon dioxide than we are able to put back into Earth's system. So it's just staying in the atmosphere. That is a forcing. Methane is another forcing. Halocarbons, these are the chlorofluorocarbons that I couldn't explain or not, I couldn't pronounce. Ozone, Nitrous oxide is a forcing. And then we have some that are negative forcings. So we might have some that help the environment, that help Earth's system. But obviously, what you can see here is that the positive forcings are overwhelming our negative forcings. And what that means is that we're putting way more into the atmosphere than we are able to put back into Earth's systems. So it's staying in Earth's atmosphere and hanging out and being in a greenhouse gas. Okay. Some major forcings in the climate are the sun. So I know that seems silly, but the sun is a forcing in that it is coming into Earth's system, but right now it's not leaving Earth's system because it is staying and warming the Earth's system of solar radiation, right? Greenhouse gases, which I talked about, and clouds are another radiative forcing. And when you have these forcings, we also talk about what we call feedbacks and how these forcings are interacting with Earth's systems in a loop. And a feedback, as a loop, is a climate feedback. A climate feedback is a process that can either amplify or reduce the effects of climate forcings. So don't panic. We're going to talk about these, talk about one each, or maybe three of one. I don't know. We're going to talk about a positive feedback. So a positive feedback creates a change, is when global warming creates a change, and some things occur within this feedback loop that speeds up the warming. So it amplifies global warming. It makes it happen faster. And then conversely, we have negative feedbacks. And these are when you have global warming that creates a change, and those items within that feedback slow down the warming and make it slower. This is a negative feedback. It reduces the effects of climate forcings. So let's look at some examples. Okay, I just want to see what's next. Okay, feedbacks versus forcings as cause for environmental change. A forcing is a primary cause of change. This is solar radiation. These are greenhouse gases. These are the things that cause the changes. It's the primary change. And a feedback is the process that is triggered by an initial change that might amplify or dampen the initial change. And between those, we have a positive feedback and a negative feedback. So remember how I talked about how we have what we call these models, right? And these models are mathematically produced data from data that we have now and have had in the past to predict what we see in the future. And we use these feedbacks that we're watching now, that we're calculating now, to predict models for the future. And that can be really hard. Models can be really difficult because you might not have all of the data you need, which is maybe why you've been seeing headlines that say, wow, the climate is changing faster than we thought, because we didn't have all the data that we thought we needed for these models. But we're doing the best we can, right, in terms of models. So that's what this was meant to explain. So most predicted climate change is the result of feedbacks, which tend to be positive for climate. And we've modeled most of these feedbacks into climate models. Okay, so what are some of these feedbacks? We're going to talk about 4 major ones. Obviously, there's like hundreds of feedbacks, thousands of feedbacks, more than thousands. I don't even know, to discuss. And it's impossible to talk about all of them, but these are the major ones that we are seeing today. The snow and ice albedo feedback, water vapor feedback, lapse rate feedback, and cloud feedback. So this is the snow and ice feedback. Sorry, I just want to see how I explain it in the slides. Okay, so this is the Arctic. Geographically, we're looking at Earth from the north, staring down at the Earth. You can see here's Alaska, here's Greenland, here's Europe and Russia and Asia and all of the continents. So we're looking directly at the North Pole on Earth. This is the Arctic ice cover. And the Arctic ice cover actually sits on top of water. And what you'll note is this was the ice edge from 1979 to 2000. The yellow was where that ice was in 2007. And this is 2012. So this was also almost a decade and a half ago. This is where the ice sat in 2012. I don't know if I have a picture of where it is now, but I can guarantee you it is significantly smaller than this. So what we're seeing is this Arctic ice melting. And what we're seeing is that it's melting at a much faster rate now than it was in 1979 to 2000. And that's because of the ice albedo feedback. The word albedo essentially means reflection. So think about the sun coming down, and if you're wearing a white shirt on a hot day, you're actually going to feel a lot less hot because the sun reflects off of the bright colors, the whiter colors will reflect off, and it will actually absorb into darker colors like black. If you're wearing a black shirt on a hot day, you're going to feel hotter than you would if you're wearing a white shirt. And that's because sunlight and the way that light waves and physics work is it absorbs into the darker colors and reflects off the brighter colors. So what we're seeing is that if we have this ice sheet, the sun is actually going to reflect off of that and go back out into space or bounce, refract, whatever. But it essentially does not get absorbed into Earth's surface, which is important. That keeps the Earth from getting too hot. But you'll note that the color of the ice sheet around the ice sheet is darker. It's blue. The ocean is a very dark entity. And so the ocean absorbs that sunlight and heats it. It heats Earth. And so what we're finding is that the sunlight is going into the ocean around the Arctic ice, heating that water, I mean, relatively, heating that water and melting the ice. And it's happening faster because as this ice sheet grows smaller, there's less reflective surface for the sun to reflect off of. So more sun can get absorbed into the ocean and melt more. Okay, so this is a feedback. So what we're seeing is warmer temperatures on the surface of Earth, which means more snow and ice will melt, meaning less snow and ice on the surface. And if we see less snow on the surface, less reflectivity will occur and more sun will absorb into the ocean, which means that we're going to continue to warm, which means that we're going to see less snow and ice, which means we're going to have even less reflectivity. And it's just, so that's the cycle. This is a positive feedback. This is a feedback that is amplifying the system. It's amplifying climate change because we're seeing warmer temperatures, less snow and ice, less reflectivity. So this is a positive feedback, okay? Water vapor. This is the second feedback. This is a water vapor feedback. So the water vapor feedback it is also, let me just jump to this one real quick. It is also a positive feedback. What we're seeing is similarly to the ice albedo, we see warmer temperatures on the surface of Earth. Because we see warmer temperatures, we see more water vapor because that water on Earth's surface is evaporating, right? Hot atmosphere is going to evaporate water and turn it into water vapor. Well, remember that water vapor is a strong greenhouse gas. So if we have more precipitation in the atmosphere, more absorption of upward surface long-wave radiation. So that's the heat that's coming out of the Earth, right? So if we see more precipitation in the atmosphere, right, more of that heat is going to bounce back into Earth, be absorbed into the atmosphere, which continues to heat the Earth. And we see warmer temperatures on the surface of Earth, which will then cause even more water vapor and water evaporation. So this shows here the temperatures that we're seeing on Earth. These are just our normal temperatures, whatever, every day, our average temperatures. So we see that there are warmer temperatures in the equator, right? We also note that there's a huge amount of water in this equatorial area. So that water is being evaporated. This side here is our humidity. This is the precipitation in the atmosphere. This is the water vapor in the atmosphere. It's all in the equatorial area, which is why you'll probably note that it's getting warmer in the equator faster than it's getting warmer up here. We're seeing higher precipitation in the equator, which is warming the equator a lot faster. Okay? This is a positive feedback. We're seeing warmer temperatures, more water vapor, which means we're keeping that heat inside Earth's atmosphere, which is going to warm those temperatures even more. Okay, positive feedback. Lapse rate feedback. Okay, this is a lot. This is a lot one. This one I think is the most confusing, so I've been reading about it all day just so I could explain it a little better, and so I wrote it all down for you. Okay, we talked about, we're mostly just going to focus on the troposphere here. I put this graph back in here, but we're looking at the troposphere. Remember, this is 10,000 meters, which is 29,000 feet. This is where airplanes fly. This is above the mountains, just a little bit. So as the atmosphere goes up in elevation, the temperature gets cooler the higher that you go in the troposphere. This is called lapse rate. As the Earth warms, because the Earth is going to be the hottest at the surface of the Earth, this is where all the heat is leaving the Earth, right? The atmosphere tends to warm up more at the surface. Where's my arrow? Here it is. More at the surface than it does higher up. But warmer air near the surface can hold more moisture, more precipitation from evaporation, and moisture is a water vapor. It's a greenhouse gas. It traps it near the ground. As the surface warms and the atmosphere above doesn't warm as much, the lapse rate, or the rate of cooling with altitude, becomes less steep. So it cools slower. This makes the climate warm even more. Where's my arrow? It keeps going away. Less cooling higher up in the atmosphere, more heat trapped closer to the surface. This extra trapped heat can lead to even more warming, which feeds back into the cycle. Oh, please. Okay, I had to pause because as I was reading this, I realized this comes across as a positive feedback. Do not be alarmed. I think it's both. This is the crazy thing about feedbacks, is they're very convoluted. It's not so black and white as saying, let's make a little cycle like this. But it's kind of both. So in a way, it is positive, oopsie, because you're trapping more heat at the surface of the Earth. And that is going to cause more heat. It's going to cause more evaporation. So similar to the water vapor feedback, in which we are evaporating, it's trapping more heat. It's doing that too. But the other thing that it is doing is, because you have this precipitation in the atmosphere, it's actually helping cool the Earth at higher altitudes as well. This one is very confusing. Don't worry, I'm not testing you crazy on this one. But you have more evaporation from the surface, which will also provide cooling. But that condensation will make its way into the atmosphere, which is higher up, and it will warm. So this slide says, yes, it is a negative feedback. I think it can be a negative and a positive feedback. But I wanted a good example of negative feedbacks, and they're really hard to find for climate science. So this is the best one I could find that I could explain. Overall, you're seeing a negative feedback because the precipitation from the water is helping cool the atmosphere, because that ocean water is going to be cold. Okay, take a breath, read over this one a few times. Note that it is both positive and negative, but for the sake of quizzes, it's going to be a negative, okay? And I say that because I want more evaporation from the surface cooling, and more condensation in the atmosphere is warming. So you have both processes here, but the overarching concept is that because we have that evaporation from the surface, it is cooling. Maybe I should fix this. It's negative. Okay. Finally, another one that I can explain really well, because this one's really cool, is our cloud albedo feedback. Now remember, albedo just means reflectivity. It means the ability to reflect. Clouds are white, mostly, right? Clouds are very reflective. And so what we see here is when clouds form from the precipitation that we are getting from the lapse rate feedback and from the what was the other one? The precipitation, water vapor feedback, pardon me. What we are seeing is these clouds forming, which help reflect sunlight back into the atmosphere. However, they also cause more radiation to be trapped underneath. Remember how I said when you go outside and it's cloudy, you feel that heat. It feels a little warmer than it would if it was clear. And that's because clouds act as insulators. So it does both. It both reflects that initial sunlight coming in, but it traps heat that is then coming out. But we consider this one a positive feedback because as we see warmer temperatures, we see more water vapor, which create more clouds. And those clouds, being a greenhouse gas, are going to re-emit long-wave radiation back into the Earth. Boop, boop, boop. There's actually so I know this one was confusing as to whether or not it is a negative or a positive, and I was like, it's kind of both. This is also kind of both. Right? It's not a perfect system. It's not so black and white because we see the sunlight being reflected off of clouds. So there are a lot of scientists that are like, well, let's make more clouds. There's a whole thing with that. Like, get into cloud physics if you want. It's actually like an impossible field, but there's a lot of people putting a lot of money into it right now. Because if you can create clouds, you're going to help reflect that sunlight, the initial solar radiation. You're going to help reflect that back out into the atmosphere, which will help slow the warming, right? But if you create those clouds, you're just re-emitting that infrared radiation that is being projected from Earth's surface back into the atmosphere. It's like, it's crazy, the sort of physics that goes into this particular feedback. I think it's a really interesting feedback. I don't know where I fall on it, honestly. Like, if I were to have a strong opinion about it one way or the other, I don't know that much about cloud physics. But you will see some scientists that are like, okay, but we should make more clouds because that's re-emitting the solar radiation back into the atmosphere, which causes cooling. Woo! But if we do that and we have these clouds, that's going to re-emit this infrared solar radiation back into the atmosphere. We're seeing cooling and we're seeing warming. Like, what the heck? Science? But we definitely see more warming than we do cooling, apparently, because we consider it a positive feedback, where we see warmer temps and we see more water vapor that cause more clouds, that create more clouds, and those clouds are going to re-emit long-wave radiation like greenhouse gases, which warm the temperatures, which create more water vapor. So this one is also a really interesting topic. And one of the things they talk about too is where can we put these clouds that will be the most productive? Like maybe if we put them higher in altitude, it won't keep that long wave radiation in as much, and it will also, reflect more sunlight. It's like crazy the conversations that climate scientists are having regarding clouds. So we're going to call this one positive because by far this one is definitely warming more than it is helping cool more. But it is a conversation. Okay, so those are feedbacks. I know that this is probably the most confusing part about climate change. However, it is a really important part because imagine doing this and then minutely understanding the concepts that go into all of these feedbacks and then understanding that there's hundreds, if not hundreds of thousands of these feedbacks that you then have to consider into climate models that will then look into the future and understand how that's going to affect climate change in the future. So that's something to, I mean, CO2 is obviously a feedback as well. The more CO2 we put into the atmosphere, the more warming, which might create more CO2. So all of these feedbacks, these climate scientists are putting into models with exact numbers and exact data sets to predict the future of climate. And that's why it's such an important thing to cover. Okay, we're almost to the end, I promise. Let's talk anomaly. So I brought this up earlier and I said it's something that deviates from what is normal, average, or expected, right? It's different than the average, different than what's normal. And you need three things to calculate anomalies. Some kind of measure of what is normal or average based on all this data, so much data. And then you have to have a measure of the item of interest for that time or place. So if we're considering a carbon dioxide anomaly, what is the normal amount of carbon dioxide? Also a conversation that scientists are having right now. And then how much of that carbon dioxide do you want for a time and place? What is a normal consistency? What is a normal amount of carbon dioxide for a specific place and a specific time? It might change. And then what is the range or variation of the average value? For your lab this week, oh gosh, I don't want to talk about that because it'll change. Well, I guess part of the lab won't ever change because I'm going to keep that the same. But you're going to consider this for your lab this week. What are anomalies? So here is the CO2 emissions concentration anomaly from 1959 to 2021. So what we're looking at is a relative anomaly relative to 1951 to 1980's mean. So that is this line right here, boop, 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 at the very bottom of this. 0. This 0 just means that there is no change based on the average relative to 1951 to 1980. Okay? That's what this means. That means if this carbon dioxide was, oh, it's over here. Ha! 335. This is what we consider average carbon dioxide from 1951 and 1980. We think, oh, well, this is where we want it. Come back, arrow. Come back. This is where we want it. This is where it should be. This is our average. This is our expected. Is 335-ish. I actually don't know. That's me estimating. This line is the average that we see of our anomaly. And this is actually measured data because we are now in 2025. This is measured data from 2020 to 2021. This is the CO2 that we have emitted every single year. And what we're noting is that from 1960 to 1980, there were some negative anomalies. That means we were emitting less CO2 those years. Interestingly, if you didn't think about it, and we're here in 2020, we emitted a lot of CO2, over 418 maybe. And then all of a sudden in 2021, it dropped really low. And you're like, what the heck? How'd that happen? You remember we were all trapped inside from a pandemic this year. And there were actually a lot of news outlets that and science people, climate science, that recorded significant drop of CO2 emissions that year because everybody was working indoors. A lot of people were laid off. So a lot of industry shut down. A lot of people, less people were driving to get to work, right? So we had a significant drop in CO2 the year of the pandemic. So if we're looking at silver linings here, that was the silver lining of the pandemic, a significant drop of CO2 emissions. But this is our anomaly. It is the change from what is expected from what we want. And you're going to look at this with lab. Okay, that's it. That's my climate chat. So sorry that it was, I'm not sorry that it was long. It was long. I know that there were some confusing topics this week, I should say. Let me stop sharing. So I know there were some confusing topics this week, and I apologize, but it is an important topic to talk about because we're going to dive a lot further into climate change for the rest of the term and how it's affecting these different other topics, like food and agriculture and water usage. So it's really important. Thanks for listening. I'm about to film another video that'll be much shorter than this regarding your lab and homework.